This is Mr. Hassan's Maths channel. Now, in this video, I'm going to just go through a bit of an explanation about the reverse of the chain rule. Now, this is something which a lot of students have issues with in P3, and it's something which is just a shortcut for certain types of questions that you can use instead of having to go through the whole process of substitution. And it makes life a lot easier in many cases. And that's the kind of method which they kind of mention in the book. They don't really expect you to know how to do substitution until P4. And, once you get used to it, it's actually very easy. Okay. And I have my own particular way of carrying out the actual calculation. But here are a few examples of questions where we can reverse the chain rule in order to do integration. Okay, so I'm going to start off with actually the ones at the bottom here. I'm going to start off with G. Okay, so here we have x e to the power of x squared. So when you're reversing the chain rule, you've got to ask yourself, you've got to have something of this form where you have a function inside another function, something like this. So you have g of f of x. So there's a function inside a main function. And multiplying that whole thing must be something of the form, of the correct form of the differential of what's inside the function. So when you're reversing the chain rule, you've got to ask yourself, what is the main function and what is multiplying the main function? So in this case here, what we can see here is the main function is e to the power of something. I can say the main function is e to the power of something. Okay, and what's inside that function is x squared. Okay, so x squared is inside the main function. So e to the power of x squared. So this is what's inside the main function. The main function is e to the power of something. And what's multiplying the function? X. Okay, so this is what's multiplying the function. Now you ask yourself, if I differentiate what's inside the function, do I get something of the same form as what's multiplying the function? Well, I do, because if I differentiate x squared, I get 2x. Outside the function is 1x. It's just a multiple of something of the right order. If it was, for example, x squared e to the power of x squared, then it wouldn't work, because outside the function is not something of the right order as the differential of what's inside the function, because x squared is not the same as, if I differentiate x squared, I get x, and that's not the same as x squared. They have to be the same power or the same type, the same type of thing. So here we can see the main function here is e to the power of something, and what's inside the function, what's outside the function is the differential of what's inside that main function. So here we have this, which we're going to integrate with respect to x, which is going to give us, now how do we integrate this? Now the way I like to do it is I like to write this thing that's multiplying with it in the beginning, and then I integrate this in the normal way. Now e to the power of x squared, e to the power of anything just integrates by staying the same. That's how you integrate something, e to the power of something. So if you integrate e to the power of x, it becomes e to the power of x. It stays the same, doesn't change whatsoever. But then you got to think about what's inside the function and divide. When you're integrating, you divide by the differential of what's inside the function. So you divide by the differential of x squared, which is 2x. Okay, and we're going to have our plus c here. And we can see here that this x and this x, they cancel out, which should always happen. You'll notice that they cancel out. What's multiplying the main function will cancel out when you divide by the differential of what's inside the function. That main thing will cancel out, and you'll be left with, in this case, e to the power of x squared over 2 plus c. And we can check. We can always check our answer by doing what? By differentiating our main function. So if you differentiate this, you have a half e to the power of x squared. Okay, it stays the same. But then you have to multiply by the differential of what's inside the function. Remember, chain rule. So you multiply by the differential of x squared, which is 2x. Okay, the c, of course, becomes 0. A half times 2, they cancel out. You're left with x times e to the power of x squared. So we can see it's exactly what we started with. So we know that this is correct now. We know that this is correct. Okay, you can always check your answer. Always you can check your answer. And the same applies, for example, to function h, or question number h, or or question H. We're going to integrate the cosine of 2x times 1 plus sine of 2x to the power of 4 with respect to x. Now, we have to ask ourselves, is it one of those type of functions where you have a function inside a function? Well, the main function here would be something raised to the power of 4. And inside that function is 1 plus sine of 2x. Okay, so that would be like your g of x would be your something to the power of 4, and f of x would be 1 plus sine 2x. That's function inside another function. And outside the function is cosine of 2x. Now, if I differentiate sine of 2x, I get 2 times the cosine of 2x. So it's a multiple of the correct form that I need. Okay, so this is of the correct form for what I need for reversing the chain rule. Okay, so the main function is something raised to the power of 4 this time. Okay, the main function here is something raised to the power of 4. How do we integrate something that is raised to the power of 4? Well, that's the type of integral where you have to add 1 to the power and divide by the new power. So, as I said, I like to write it out as it is. So I put cosine of 2x. I write this without any change, 1 plus sine 2x. But then I raise the power by 1, divide by the new power, and then again, when you finish doing the main integration, you have to then divide by the differential of what's inside the function. So when you differentiate sine of 2x, you get 2 cosine 2x. And don't forget the plus c. So again, we'll notice what happens here. This cosine 2x cancel with the cosine 2x. Most people don't actually write this step. I like to do it to see they cancel out and rest assured that I've done the right thing. So this gives you 1 over 10, because 5 times 2 is 10, times 1 plus sine of 2x to the power of 5 plus c. And how do we know and be rest assured that we've done the right thing? Well, we can check by differentiating our answer. If we differentiate this, we have to multiply by the power and take 1 from the power. So you have 5 over 10 times 1 plus sine of 2x to the power of 4. Then we multiply by the differential of what's inside the function. Now if you differentiate sine of 2x, we get 2 cosine 2x. And the c, of course, cancels out. So this 5 and this 2 and the 10 cancel to give you 5. 5 cancels with the 5. And you're left with cosine of 2x times 1 plus sine of 2x to the power of 4, which is exactly what we started with. So this check shows that we were correct, and this is the correct answer. Okay, so this is a check you can do to make sure that it takes us back to what we actually started with, so we know that we've done the right thing. When you differentiate this, you get exactly what we started with. Okay, because remember, the integration and differentiation are inverses. So that's example H. Let's go to example I. Okay, so let's come in the right place actually. So I is secant squared x times tan squared x. So here you've got to integrate secant squared x times tan squared x with respect to x. Now, how can we recognize this as something which is the reverse of the chain rule? All right, so what we can do is we can think of, for example, I know that the differential of tan x is sec squared x. Okay, so I can think of this as this is being the integral of, I've got tan x. Now I like to write it like this to make it clear. This is like tan x to the power of 2. Okay, this is tan squared x. So the main function here is something raised to the power of 2, and outside the function is the differential of what's inside the function. So you have sec squared x on the outside. If I differentiate tan x, what do I get? Sec squared x. That's inside this function. So again, the type of function it is something raised to the power of 2. Inside it is tan of x. Outside it is the differential of tan x, which is sec squared of x. Okay, so it's of this form that we need, where you have a main function, and inside it, when you differentiate, you get what's multiplying the main function. Okay, so now what we can do is exactly the same as before. As I said, most people don't do this, but I like to write this down, sec squared x. Then I'm going to take this and I'm going to raise the power by 1, divide by the new power, and then also divide by the differential of what's inside the function. If I differentiate tan x, I get sec squared x, and I've got my plus c. This cancels with this, so we're left with 1/3 tan. Now we can write it as cubed x plus c. And again, when we check our answer, if you differentiate this, multiply by the power, so you have 3 times 1/3. Take 1 from the power, so it's going to be tan squared x, and multiply by the differential of what's inside the function. Remember, it's like inside it's tan x, you multiply by the differential of tan x, which is sec squared x. So the 3 cancels with the 3, and we're left with exactly sec squared x times tan squared x. So there's that part here. Now somebody might think, how about if we think of this as this being like the main function, and this being multiplying the main function. So you could, for example, think of this as being secant squared x times tan squared x, and rewrite it as, for example, secant x tan x. Okay, secant x times tan x, and then you have secant x times tan x. So it's not going to work here because you're going to have a tan squared. All right, so if you think of secant x being the main function, you have secant x times tan squared x. That's not the form of the differential what's inside, so we can't do it that way. So that doesn't work. Okay, so it has to be this way here. Okay, so that's that question. Right, just a little bit of practice there. Now I'm going to go to part J. Let's do J. We got secant squared x and 1 plus tan squared x. Let's have a look at how that would work. Okay, so here we have the integral of secant squared x, secant squared x, and 1 plus tan squared x. All right, now in this case, it's not quite the same, because if I think of the differential of what's inside here, it's not going to give me secant squared. This is 1 plus tan squared x. It's not tan x. If it was 1 plus tan x, then that would be correct. That would be something that we could use the reverse of the chain rule. So what I'm going to do here is I'm going to actually expand this. So this gives me secant squared x, and then I'm going to have plus, and this will be now secant squared x times tan squared x with respect to x. Now I know the integral of secant squared x is tan x. All right, that's just one of the basic results. All right, so this is going to give me tan of x plus, and now I can integrate this. Now I can think of this here as secant squared x as being outside the function, and the main function being tan x all squared. So it's something squared. This is tan squared x, which is tan x all squared. So this is like the main function in this case is something squared. What's inside it is tan x, and what's outside is the differential of tan x. So I can use the reverse of the chain rule for this part. So that I'm going to have tan x, which is from that being integrated, plus, and as I said, I like to write this in this way, sec squared x. I'm going to increase the power by 1, so it's tan x all to the power of 3, divide by the new power, and then multiply the denominator here, or divide by the differential of what's inside the function. Differential of tan x is sec squared x, and as we know, these cancel out, and we're left with tan x plus 1 over 3, and this will be tan cubed x plus c. And if you were to differentiate this, what would we get? This would give us sec squared x, and this would give us 3 times 1 over 3 tan squared x, and then I have to multiply by the differential of what's inside there, sec squared x. They cancel out. I'm left with sec squared plus tan squared x sec squared x, which is the same as this. Take that as common. Sec squared 1 plus tan squared x. So yes, that gives us the right answer. Okay, so here's our answer there. So again, differentiating your answer always to check to make sure. So those are these type here that I've just answered first. G, H, and I, and J. All right, so here you have a function inside another function, and that's how they work. Okay, now I'm going to go to A, B, C, D, E, F, and I'll do all of them just as a practice to make sure everyone understands what's going on. Okay, so now we're going to go through these other ones. So I'm going to start with A. So here we have something which is slightly different. We have x over x squared plus 4. We're going to integrate this with respect to x. In this case, when you have a fraction, what we're looking out for is something of the form where the numerator is of the form of the differential of what's in the denominator. Okay, if that's the case, then this will integrate to be ln of the modulus of what's in the denominator of that form. Okay, so when you see this, and the reason behind this, for example, if we know we got, if you want to differentiate ln x, with respect to x, we get 1 over x. And if you have a function inside that function, for example, ln of, say, x cubed, if you differentiate ln of x cubed with respect to x, you get 1 over whatever's inside that function, which is x cubed, and then you multiply by the differential of what's inside here, which gives you 3x squared. So you start off like this. Okay, so you end up with something on top, which is the differential of what's underneath. Okay, so that's the reason why. So let me make it a bit clearer. If it was ln x cubed plus 1, for example, and you differentiate that, you're going to have 1 over x cubed plus 1 times, and then the differential what's inside the function, which will be 3x squared. So you end up with 3x squared over x cubed plus 1. So we notice that the numerator is the differential of what's in the denominator. Okay, so we can reverse the chain rule by going backwards. Okay, just like we did with these. But in this case, it's when you have a fraction, it's the result. When you end up with a fraction and the denominator, it's the result of the ln of something being differentiated if the numerator is of the form of the differential of what's in the denominator. Okay, so that's what we have to understand here, right? So for A, we could notice that same pattern. It doesn't have to be exactly the same. Like if I differentiate x squared plus 4, I'm going to get 2x, but it has to be of the right order. Now 2x is a linear, okay, and x is a linear, and the 2x is a multiple of x. So this can work. This was going to be, and as I said, the way I like to write it is I write this as it is, the numerator part, and then I'll write the ln of the modulus of x squared plus 4, and then I divide by the differential of what's inside the function, which is 2x. And I've got plus c at the end. So how does 1 over something integrate? It becomes a ln of that thing. So you have x times the ln of x squared plus 4 over the differential of what's inside the function, which is 2x. The x's cancel out, and we're left with a half times the ln of x squared plus 4 plus c. And it only works if the numerator is of the form of the differential of the denominator. For example, if that was x squared on top, it wouldn't work. If we tried to do this, it wouldn't work, and one of the x's wouldn't cancel out. And if you differentiated x squared over x squared plus 4, well, that won't give you, if you try to differentiate the answer that you got, it won't give you this, because you'll have an x there. It will be like you have to use a product rule to differentiate this to give you that, right? It won't work. If it was x squared up there, you'd end up with an x here, and it won't be the same, so that can't be the integral, right? But here, if we integrate there, if we differentiate our answer, if we differentiate this answer, what do we get? Differentiate something like this, so you have a half. This becomes 1 over x squared plus 4, 1 over whatever is inside there. Then you multiply by the differential of what's inside the function, which is 2x. The 2's cancel out. You're left with x over x squared plus 4. The c becomes 0. And you're left with exactly what we started for. This is like our check. This is not the actual part of the answer. This is just a check, right? So that's how that works. I'll show you, for example, part B. Okay, we've got B. We have e to the power of 2x over, and here we have e to the power of 2x plus 1. Want to integrate this with respect to x. Again, we see that if we differentiate the denominator, we get some form of e to the power of 2x. We get 2e to the power of 2x. So this is the correct form. The numerator is of the right order, the right form of the differential of the denominator. So I'm going to integrate it as follows. As I said, I like to write this thing always and see that it cancels. So e to the power of 2x times the ln of the modulus of e to the power of 2x plus 1. And then I always divide by the differential of what's inside the function. So I'm going to divide by 2e to the power of 2x, because when you differentiate e to the power of 2x, you get e to the power of 2x, but then you multiply by 2 for the chain rule, and then plus c. Now e to the power of 2x cancels out, so we're left with a half ln of the modulus of e to the power of 2x plus 1 plus c. Now we can check our answer again to make sure that we've done the right thing by differentiating this. Now if you differentiate this, what happens? You have 1 over 2, this becomes 1 over e to the power of 2x plus 1, and then you multiply by the differential of what's inside there, which is 2e to the power of 2x, and the 2's cancel, and you're left with e to the power of 2x over e to the power of 2x plus 1, which is exactly, again, what we started with. So the check always is a good idea for you to make sure that you have done the right thing. All right? So there we have the answer to part B. And I'm going to go through part C as well. So we have x over x squared plus 4 cubed. So C is x over x squared plus 4 cubed. Now this one is slightly different because the numerator is not the differential of the denominator. Okay, so this one, what I'm going to do here, even though it's a fraction, I'm going to rewrite it as x times x squared plus 4 to the power of negative 3 with respect to x. If there's a power of 1 here, then you can't do this. Because when you try to integrate, you add 1 to the power, you get 0. And divide by the power, divide by 0, it doesn't work. It messes up. That's why we use lit, right? So you have something like this, okay? We're going to try to integrate it in this form here, in this way here. If it was x squared plus 4 only to the power of 1, yes, the numerator is of the form of the differential of the denominator. But right now it's not. It's not a question of what's inside the function. It's actually, this should be the differential of the denominator itself. So this is going to have a similar form to what we were looking at before. Now we have the main function is something to the power of negative 3. Inside the function is x squared plus 4. And multiplying the function is something of the form of the differential of what's inside the function. So I don't need any of this in this question at all. Okay. So what I'm going to do now is I'm going to say, okay, so we're going to take I'm going to write the x there as always. I'm going to take this as it is. I'm going to add 1 to the power, so it becomes minus 2, divide by the new power, which is minus 2, and then multiply the denominator by, or you can say divide by the differential of what's inside the function, which is 2x. Okay, so the x cancels, got your plus c, so that gives you minus 1 over 4 x squared plus 4 to the power of minus 2 plus c. And how do we know we're right? We do a little check. So if we check, we multiply by the power, minus 2 times minus a quarter is going to be a half, positive a half. You have x squared plus 4. You take 1 from the power, so that's going to become negative 3. You take 1 from the power, negative 3. And then you multiply by the differential of what's inside the function, which is 2x. All right, the c cancels out, and you're left with the 2 cancelling with the 2 here, and you're left with x times x squared plus 4 to the power of negative 3, which is the same as x over x squared plus 4 all cubed, which is exactly what we started with. Okay, so we can be sure that we've done the right thing and we've done this differentiation. So that's part C done. Okay, so that's that part C. Now for part D, very similar. Okay, part D, do I have space? Yes, I do. Part D is quite similar. All right, you have e to the power of 2x over e to the power of 2x plus 1 cubed. Okay, so this time you have e to the power of 2x over e to the power of 2x plus 1 cubed with respect to x. So again, in this kind of question, the numerator is not the differential of what's in the denominator. Okay, but we can rewrite this as e to the power of 2x times e to the power of 2x plus 1 to the power of negative 3. And we can integrate that with respect to x. And we notice that if I differentiate e to the power of 2x plus 1, I get e to the power of 2x, some form of e to the power of 2x. So the main function again is something here to the power of negative 3, and inside it is e to the power of 2x plus 1, and outside it is e to the power of 2x. So I can use the reverse of the chain rule. So I'm going to write e to the power of 2x outside. I'm going to leave this as it is, but then I'm going to add 1 to the power, so it becomes minus 2, divide by the new power, minus 2, times the differential of what's inside the function, which is 2e to the power of 2x. So I end up with minus a quarter, and the e to the power of 2x cancels. I have e to the power of 2x plus 1 to the power of negative 2 plus c. And there's my answer. And I can check my answer by differentiating this. If I differentiate this, I multiply by the power, so I get positive a half, e to the power of 2x plus 1, take 1 from the power to the power of negative 3, times the differential of what's inside the function, which is 2e to the power of 2x. 2 cancels with the half, and you're left with e to the power of 2x over e to the power of 2x plus 1 cubed, which is exactly what we started with. All right, but this is our answer to that question. That's just our way of checking. All right, so that's another example, okay, from part D. And now I'm going to go through these two trig examples just to give a bit more practice. So now I'm going to go through part E. We have to integrate with respect to x the cosine of 2x over 3 plus sine of 2x, sorry. Three plus the sine of 2x with respect to x. So this is a case where, yes, the numerator is of the form of the differential of the denominator. And if I try to write it like this, okay, 3 plus sine 2x to the power of minus 1, and I try to proceed like this, I'll face a problem when I try to integrate it, because then I have to add 1 to the power, and this will become a power of 0 divided by 0, and it will break down. So I can't do it like that when there's no power there. Okay, when there's no power there, when it's not a bracket like these other ones like this and this. I have to use this Lin method, so I have to make sure that the numerator is of the form of the differential of the denominator. I differentiate 3, get 0, differentiate sine 2x, I get 2 cosine 2x, so this is of the right form. So what I'm going to do, as I like to do, I'll write the cosine 2x, and then I'll write ln of the modulus of this as it is first, 3 plus sine 2x, and then I'm going to divide by the differential of what's inside the function, which gives me 2 cosine of 2x. They cancel out. I've got my plus c. So I'm left with a half times the ln of 3 plus sine of 2x modulus plus c. And if I differentiate this, I'm going to have a half times, and I put 1 over whatever's inside the function, 3 plus sine of 2x, multiplied by the differential of what's inside the function, which is 2 cosine 2x. Half cancels with the 2. We're left with cosine 2x over 3 plus sine 2x, exactly what we started. Right, so I know that this is the correct answer. This is just like our check. And for the final question F, we have the sine of 2x over 3 plus the cosine of 2x, and this time all cubed. I want to integrate this with respect to x. So in this case here, it's the case where, if I differentiate this, I don't get sine 2x. I'll have, this chain rule thing to do. So it's not going to work in that same way, but I know that sine 2x is a differential of cosine 2x, or of the right form of it at least. So I can rewrite this as this other type where I have something multiplied by a function, okay, and what's inside that function, when you differentiate, you get what's outside the function. So if I differentiate cosine 2x, I get something of the form of sine 2x. And this is going to be to the power of negative 3 because it's in the numerator now. I want to integrate that with respect to x. So now what I'm going to do, I recognize it's of that form where this is the differential. This is like, say this is the main function is f of something. So inside the function is gx. Outside the function is the differential of gx. It's that type of form. So here, what I'll do is I'll write my main function, I'll write sine 2x, and then I'll start to integrate this. So I'll put 3 plus the cosine of 2x, add 1 to the power, divide by the new power, and also divide by the differential of cosine 2x, which is minus 2 sine 2x. If you differentiate cosine of something, you get minus sine of the same thing, but then you have to multiply by the differential of what's inside the function, and then I'll have my plus c. So here we'll notice the sine 2x is cancelled out. Minus 2 times minus 2 is plus 2, is plus 4, sorry, so you have a quarter. 3 plus cosine of 2x to the power of negative 2 plus c. Okay, and if we want to make sure of our answer, we can differentiate this. So we multiply by the power, minus 2 times a quarter, and then we take 1 from the power, so 3 plus cosine of 2x to the power of negative 3, if you take 1 from the power, multiplied by the differential of what's inside the function, which is going to be negative 2 sine of 2x. So what happens here is the minus and the minus becomes a plus and cancels with the plus 4, and you're left with sine of 2x times 3 plus cosine of 2x to the power of negative 3, which we can rewrite as sine of 2x over 3 plus cosine of 2x, all cubed. Okay, so this is our check, so we know that this is the correct answer. When you differentiate it, we get what we started with. All right, so that's just a little summary of a few types of questions which hopefully give you the right idea of how to deal with reversing the chain rule. Okay, so I hope that was useful. Okay, and of course, there's plenty of other examples that we could go through, but I hope that gave you an idea of how to deal with it. Thank you for watching. Other questions from this particular chapter of the textbook, you'll find in the playlist that will appear over here. I probably answered a few of these questions previously, maybe, I'm not sure, but you'll find other questions from this chapter of the textbook in the playlist over here. You will find questions dealing with integration of P3 in this playlist over here. You can subscribe to my channel by clicking on this link, and you can use the video over here to help you navigate through my channel to find what you're looking for. Thank you for watching, and see you soon.